Alright guys, we are actually going to be talking about the gas laws today, and this is Chapter 3, Section 2. And so as we're looking at these gas laws, there are going to be 4 gas laws that we are going to talk about. One of them is actually taking some of the other gas laws and putting them together. Okay, so as you are going through this set of notes, it's going to be the blue writing that is going to be really beneficial to write down. So anytime you see any blue writing, you're going to see that specifically a lot of these gas laws are going to be dealing with pressure, volume, and temperature. Alright, first before we get to some of that, we got to go through some basic terminology. So first of all, like I was mentioning, pressure, volume, temperature, as long as you guys know what those are, you're in pretty decent shape. If not, then it'd be beneficial to learn some of that. So that's what we're going to go through first. So I would highly recommend writing down these vocab terms, and if at any point you need to pause the video or have anyone pause it, then you certainly can do that. That way you can get all the information you possibly need. Alright, so how many of you have ever seen a hot air balloon? Yeah? How about had a soda bottle spray all over you, or pop if you prefer pop? Or how about baked or eaten a nice fluffy cake? And so these are all examples of gases at work. And so when we're looking at gases, what we're going to be seeing is that gases actually, like we mentioned in the previous video, they expand. They have a lot of kinetic energy. So as they do so, then they are going to be having specific properties. And so that's what we're going to be observing here is the properties relating to pressure, volume, and temperature, because they are all going to directly affect one another in different various ways. Okay? And so let's get into some of our terminology. So first of all, we could talk about, like I said, pressure, volume, temperature, but you can see that I have an additional one in here, and that additional one is the amount of moles, and we've already seen that in Chapter 1. You guys remember our 7 base units, and so the amount of moles was one of those base units. Alright, so before we move on, what we're going to do is we are going to be labeling, actually, no, we'll do this as we go through. It makes it a little bit easier. So what we're going to do is we're going to be going through each one individually. So we're going to be starting with pressure. We're going to learn about what it is and what it actually entails, what the units would be, and how it directly affects some of the others. Alright. So pressure, like I said, the blue writing is going to be important to write down, and you don't need the black writing at the bottom, that's fine. So pressure is defined as the force the gas exerts on a given area of the container in which it's contained. Okay, so specifically the key here is that it's a force exerted on a given area. So if I wanted to, I can actually create an equation, and pressure is related to the force. I guess I'll do all capital letters here. Force divided by the given area. And you're going to notice a lot of these equations that we're going to be learning here coming up are all going to be just three variables in the equation. And we mentioned before these SI units. Now this is an SI unit, it's not an SI base unit, and that's the difference between those 7 base units and units like this. And so the unit is called a Pascal. Okay, and so as we're looking at a Pascal, that is 1 unit of pressure. So if I looked at the equation I have up top here, force is going to be measured in what we're going to call newtons, and area, as we learned before, the base unit of length is a meter, so therefore area is length times width, so it's a meter squared on the bottom. And a newton per meter squared is what is equal to a Pascal. Okay, so newton per meter squared is equal to a Pascal, which would be important to write down. Other things that we're going to write down, some of the other units of pressure that you may see would be what is called a torr, T-O-R-R, and you also have millimeters of mercury, which is mmHg. Let me see if I can put a little line on there. There we go. So we have torr, which is T-O-R-R. We have millimeters of mercury. We also have something called an atmosphere, which is abbreviated ATM. Wow, that was a bad M. So let's see if I can fix that for you. So We have torr, millimeters of mercury, and atmospheres. Those are some of the 3 other main units that you may see in terms of pressures. Now, I will tell you that depending on pressures, you don't necessarily have to convert them as long as you have the same units when we're working in these equations. You might also see this other one, which is pounds per square inch. And you've probably seen that one before. It's known as PSI. And so you probably heard or seen PSIs. A lot of times the tires on your car are measured in PSIs. Alright, so that's pressure. Now we can talk about volume. And so volume, you probably have seen it before, you know what it is, which is why I have the definition and equation here pretty short. So volume is a 3-dimensional space inside the container holding the gas. And like I said, it's an SI unit. It's not an SI base unit. So the SI unit for volume is a cubic meter. However, you can see I also might include liters. So volume, once again, is length times width times height. And naturally, each of these would be in meters times meters times meters, which would give me meters cubed. And so then that's what I would have for my main unit that I could use. However, volume, once again, so it can be in meters cubed. It could also be in liters. You might see it in milliliters. You might see it in, let's see, cubic centimeters, also known as cc's, which could also be written as cm cubed. Let's see, you could technically use any volume unit depending on what you're given, and so these are just some of the common ones that you may see. Okay, so once again, 3-dimensional space. Alright, that moves us on to amount of moles, or the amount of a substance, and you guys have seen this before. So the amount of substance, once again, it is an SI unit. This is actually an SI base unit. And remember that we talked about moles in chapter 1. We can't count molecules because they are super tiny. So instead what we do is we want to use something called a mole. Because a mole, if you remember Avogadro's number, it's kind of at the bottom right here. 6.022 times 10 to the 23 particles, and it could be particles, it could be atoms, could be molecules, could be whatever you actually are looking at or observing. It could be couch cushions, it could be candles, it could be, let's see, students, it could be desks, it could be whatever you're counting. It's just a number to count by, okay? And since we can't count, we're going to convert our measured masses, which what we're going to do in a couple chapters, to the number of moles. In doing so, using the molecular formula, weight of the gas, what we can actually do is we are going to be converting from mass to moles, moles to mass, and then later we will use those to be able to find, use that in the gas laws, since we have to know the number of moles to be able to insert it into different kind of laws. Alright, so the amount of moles, I put an equal sign, it's just basically equal to the bottom, what you got there for Avogadro's number. Alright, last thing is temperature. We've already discussed temperature, what it's typically measured in. Your standard unit is going to be Kelvin. So you can see at the bottom here I have that it's going to be measured in Kelvin. So it's described as a measure of kinetic energy, and that's the key, that temperature is kinetic energy. So depending if you have a lot of kinetic energy, that means that you're going to have something at a very high temperature. Standard units have to be in Kelvin. This is like super important right here. So make sure you have that. Standard units are required for these calculations, so you have to be using Kelvin. It's required. So if your temperature is not in Kelvin, you need to convert it. And if you are in Celsius, to convert from Celsius to Kelvin, you just add 273.15. And if you were going from Celsius to Fahrenheit or Fahrenheit to Celsius, I could give you a couple of those conversions as well. So if I was wanting to go from Celsius or Fahrenheit to Celsius, then I would say Celsius is equal to 5/9 times F minus 32. would be your equation for that. I believe I left out the parenthesis here. Yeah. So you're going to have Celsius equals 5/9 times the parenthesis or quantity of F minus 32. So if I did a quick kind of calculation, let's say that I was trying to convert, let's just do 98 degrees. We'll do 98.6 since that is, you know, the standard temperature for a human being. So if I did 98.6 and I'd be subtracting off 32. So this quantity right there, I'd have 5/9 times 98.6 minus 32 gives me 66.6 degrees, or, well, I guess it's not degrees anymore. So if I then multiplied that by 5/9, so you could just do like times 5 and then divide it by 9 if you're using like a simple calculator, and that gives me about 37 degrees Celsius. So when I'm looking at temperatures, I know that 0 degrees Celsius is freezing. 37 is actually a really hot temperature, but it doesn't seem like it. It's kind of low. So that's a conversion that you could use to convert from Celsius to Fahrenheit. So now, if I gave you a temperature in Fahrenheit, you could then go to Celsius, and then once you're in Celsius, you add 273.15, and you'd be in Kelvin. So I could take 37 plus 273.15, and that would mean that this temperature in Kelvin would have been 310.15. Okay, so all your temperatures have to be in Kelvin. The other units of pressure and volume, it does not matter. Just make sure they match up. All right. So some relationships with gases may be easy to predict. Some are more subtle. So what we're going to do is we're going to look at each and every single one of these gas laws. And the first one is going to be Boyle's law. And so when we're talking about Boyle's law, you can see that what I have on this front slide, and this will come up a little bit later, but it's a relationship between pressure and volume. So Boyle's law, think P and V. That's important. So Boyle's law is pressure and volume. Okay? So that means that pressure and volume are going to be in this equation, which means which variable is missing. So we got, remember, we're going to have pressure, volume, temperature, and number of moles, which I'm going to use a lowercase n because that's usually what it is in these equations. So that means that temperature is not in this equation, and neither is the number of moles. Okay, so that means that those two must be held constant. All right. So this law is named for Charles Boyle, who studied the relationship between pressure and volume in the mid-1600s. The equation, it will come up on the next slide, so you don't need to write this equation that I got right here, but you can write the equation that's going to be coming down. So it says Boyle determined that for the same amount of gas at a constant temperature. So this idea of same amount of gas, that means that the number of moles, that n, is a constant. And naturally the same temperature, so temperature is also a constant. This is called an inverse relationship. So that means that as one goes up, the other one goes down. So if I was to take pressure and I was increasing pressure on a gas, so it's like you're pushing more on the molecules, then you can cause the volume to decrease as long as you kept the temperature constant. So in doing so, it's like basically saying, all right, I'm going to put a lot of pressure on the same number of molecules, and in doing so, I'm going to be able to compress it into a smaller space. Okay, so let me show you what I mean. So in the next picture, what you're going to see is there's going to be a cylinder and there's going to be a piston, and what it's going to do is it's going to pressurize the gas particles. So as I kind of turn the slide here, you can see the gas particles inside are going to be pressurized, so you're adding more mass. The green mass is on top, so you add more mass, which increases this pressure gauge, and as the pressure increases, then check out the space here. So originally the box was at 4, and then it drops all the way down to 2, so we are compressing that space by almost half. or compressing it into a space that is half of what it originally was. And so you can see then this curve over here, the graph, it has V or volume on the y-axis, has P or pressure on the x-axis, and I can see that that is considered an inverse relationship the way that graph actually goes, because it says as pressure increases or moves from left to right, then the volume is actually decreasing going from top to bottom. All right, so we're going to kind of get into the equation for Boyle's law. You can see none of this is blue. We're not writing any of it down. And so if you know the initial pressure and volume and have a target value for one of the other variables, you can predict what it's actually going to be as long as your temperature is constant. Okay, so here's your general equation. This is what I want you to write down. You can see it's all in blue. So when we're looking at Boyle's law, we have these subscripts. And so as I look at the subscripts here, I can see that the first one, we have P1 and we have V1, and that means that these are the initial pressures and the initial volumes. And so that's what you can see that I kind of labeled it here. So if you kind of already get an idea what 1 means and what 2 means, you don't have to write these 4 over here. You can just kind of leave those out. And then I got P2 and V2, which means that would be your second pressure and your second volume, so those are the finals. And so naturally, since this is an equation that has 4 variables, as long as you know 3 of the variables, you can solve for the 4th one. And that's what it says at the bottom. All right, so once again, pause it at any time, and that way you can kind of jot down any of these when you need them. All right, so let's get an example and let's see kind of how it goes here. So as I'm looking at this, I know that I have P1, and this would be given in a problem. It would say like the amount of pressure on the particles in a balloon are 1 kPa, and kPa here, since it's a new unit, I forgot to mention that one earlier, is a kilopascal, which, I mean, you guys should just be like, oh, okay, well that makes sense, because kilopascal would be 1,000 pascals. So kPa is a kilopascal. As long as they're both in kPa's, like I said, the pressure doesn't have to change. The only one that would have to change is temperature, which is not even in this equation. So it'd say like there's 1 kilopascal of pressure acting on the particles in a balloon. If 4 liters, or of a 4-liter balloon, if I then increase the pressure to 2 kilopascals, then I'm asking how much volume would be in the container or in the balloon again. So ultimately all I would do is then look at, all right, the kilopascals of 1 and the 4 liters were given initially, so that was what the balloon was initially before I then changed the pressure, which would be finally, so I'm looking for the final volume. So I just plug my numbers in. So I plug in a 1 for P1, and I plug in a 4 for V1, and then for P2 I'm going to plug in a 2, and then I would just be multiplying times V2. And if you wanted, you could make that variable x, it doesn't matter. 1 times 4 is 4 last time I checked. 2 times V2 is just 2V2. And naturally, you're going to divide both sides by 2. And by dividing 2's on that side cancels, so V2 equals 4 divided by 2, which is 2. And to find the units, just kind of look up where the V1 was and see that it's in liters, so therefore that makes this one also in liters. Your unit should match what your other volume unit was or pressure unit, whatever it would be. Okay, so these are pretty easy in terms of whenever I just give you the numbers. It gets a little harder whenever I add in the words and put it into word problem form, which will happen in one of the in-class videos that you'll see later on in your course website if you go to the course website and check those out. All right. Equation number 2 is Charles' law. Charles' law is going to describe the relationship between, this time it's going to be volume and temperature. So then if I wrote those 4 variables up here again, P, V, T, and N in the same order that I had them before. So if I'm looking at volume and temperature as being part of the equation here, then I can see that pressure is not part of this equation, and once again the number of moles. So that means that pressure and the number of moles are being held constant for Charles' law. So we are just looking directly at how volume affects temperature. All right. So this law is named for a guy named Jacques Charles. So that would make him French, and he studied the relationship between volume and temperature. This was around the turn of the 19th century. You don't need to know dates, which is why I just blacked that portion out and left the rest of it blue. So he determined that for the same amount of gas at a constant pressure. So I'm going to stop there again. And so I can see that same amount of gas. So once again, that is talking about that variable N, or the number of moles. And also, it's a constant pressure. So we are not changing the pressure. So you would see words in the problem like saying, if the pressure is held constant, or without changing the pressure, something like that. So you'd know that we're dealing with Charles' law. And Charles' law is going to have a relationship between volume and temperature. It's going to be what is called a direct relationship, which means that as one goes up, the other one is also going to go up. So if I was to say have a balloon, let's see, a balloon shape, that's not bad. If I have a balloon and I was to say look at the relationship between volume and temperature, so let's say I took this balloon and then I stuck it into a refrigerator, because everybody likes to do that, right? So you stick it into a refrigerator, and in doing so what happens is the refrigerator is a lot colder. So what's going to happen to the particles inside is they're going to stop moving so quickly, and if they're not moving as quickly, then this volume is actually going to shrink. And so the balloon, as the temperature, so the temperature of the fridge would be less, then that means that the volume would also be less. Okay, so it's a direct relationship between those. Alright, and so that's kind of what it talks about on here. So suppose you have the same cylinder once again, except for this time we're going to adjust the volume and temperature. We're going to keep that pressure constant. And so I can see kind of in this picture, this time you can see that my pressure gauge is stuck. We're not moving it from 1.5. I'm guessing this would be 1.5 atmospheres based on the number that I see there. And so you can see that what I'm doing is I'm changing the temperature here. So I'm increasing the temperature by adding in the flame. And as you add in the flame, look at the particle spacing. So they're really cramped whenever they're down at the 2, or actually right above the 2. But then what happens is as the particles get hotter or increase in temperature, they gain kinetic energy and they cause the volume of the container to expand. And so you can see then on the graph on the right side, as the volume is on the y-axis and temperature is on the x-axis, as the temperature increased, the volume also increased. And it's linear increase, so therefore that's why it's called a direct relationship. Okay, and so now we can get into the equation for Charles' law. This is talking about how we're looking at temperature and volume, so as long as I once again know the initial temperature and volume, I can find the target value again. So you can see that here is Charles' law. We have V1 over T1 equals V2 over T2. You can see that it kind of has the same relationship or idea where I'm using these 1s and 2s. So the 1s once again represent the initials, and the 2s once again are going to represent those finals. So I can see that in this case, since it's a direct relationship, I can see one is going to be on top of the other. Kind of like fractions. If I had a fraction of 1/2, then if I was to say that my volume is 2, that means that the temperature would have to be 4, because this has to keep the same. So what you'll notice is if 1 goes to 2, 2 goes to 4, so they both increase in order to keep that fraction exactly the same. So that is what is considered a direct relationship, when they both will increase or both will decrease. Alright, so here's an equation, example problem and everything. That way we can try some of these. And as I'm looking at Charles' law, I can see that once again the equation is V1 over T1 equals V2 over T2. And so as I'm looking at these, I can see that my V1 is given as 2.5 liters, my V2 is given as 4.5 liters. And so I would say in this one that I have a sealed container of helium. And so that I have 2.5 liters of helium at 250 Kelvin. And then what I'm saying is I'm going to change the container of that helium, and I'm going to increase its volume to 4.5 liters. In doing so, I'm wanting to know what that new temperature is going to be. So I would plug in my numbers. So I have 2.5 over my T1, which is given as 250. Notice it's already in Kelvin, so I don't have to convert it. And then V2 is given as 4.5. And T2 is my unknown. You could label it as X once again, or I'm just going to use it as T2. Alright, so this is what is called a proportion, and I can see that it's a relationship or a comparison between two fractions, and so these fractions I can see are set equal to each other, and in order to solve that I would cross multiply. So I'm going to multiply the 2.5 times the T2, and I'm going to multiply the 250 times the 4.5. So the first one I'm going to do is 250 times the 4.5, and that's going to give me 1,125. So I get 1,125. Oops, that's a weird 5. There we go. Okay. And then on this side, it's just going to be 2.5 times T2. So naturally, these are multiplied, which means in order to solve, I want to divide the 2.5. So notice that multiplication and division are opposites of one another, and I can divide by 2.5, and whenever I do that, my T2 will come out to be 450. And it's 450. Once again, come back up here. I can see that T1 was in Kelvin, so T2 is also in Kelvin. And your temperatures should all be in Kelvin whenever you are finished with these. So that comes out to 450 Kelvin. Alright, that brings us to our third law, and this is called a Montan's Law. Sometimes people call it the Gay-Lussac Law, just because of the different scientists that actually discovered it. So Gay-Lussac actually came up with or worked with a lot of these ideas, but a Montan is the one that did the groundwork. He's the one who actually did like pretty much all the information here. So a lot of times this law is credited to Gay-Lussac because he's kind of like did the very last step or stage of it. But I consider it to be a Montan's Law. So you might have heard either one of those names for this law. Alright, and this law is named for Guillaume Montan, who studied the relationship between pressure and temperature. I guess I left out the word between there. And so as we're looking at pressure and temperature for this one, then I can see that if I wrote my P, V, T, and N, then once again this is a relationship between pressure and temperature, so volume is gone and the number of moles. So that means that volume and the number of moles should have been held constant, and it says for the same amount of a gas, which would be once again N, and a constant volume. So I am keeping volume constant as well, and it gives me a relationship between pressure and temperature. It's a direct relationship, just like Charles' law was. So that means that as pressure increases, then temperature would also increase, as long as you kept the volume constant. So this would be like, say, you have a cylinder of helium gas that you would, like fill up like balloons with at a store or something like that. And so what we're saying is we're going to keep the volume the same, so we're not changing the cylinder, but instead what I'm going to do is I'm going to increase the temperature. So if I increase or raise the temperature of the particles inside that container, think about it this way, that if you increase the temperature, those particles are going to be gaining some kinetic energy. If they're gaining kinetic energy, they're going to be hitting the walls of that container a lot more, which is then in turn going to increase that pressure, because that's really what gas pressure is how much those particles are actually hitting the walls of the container. So that's what a Montan's law does. Alright, and once again, a Montan's law, we could look at, as long as you know an initial temperature and pressure, then you should be able to find the final temperature or pressure. So here's our equation, and you can see it's very similar to Charles' law, where we have the initials again, so it's P1 over T1 equals P2 over T2. Okay, and so once again, these are the initials, these are the finals, and as long as you're able to find two of those, you should be able to move on and find, or as long as you know three of them, you should be able to move on to find that fourth one. And so that's what we're going to be doing on the next slide. Okay, so this one, if I have container of helium at 3.5 atmospheres and the temperature inside the container is 100 Kelvin, what happens to the pressure inside the container if I increase the temperature to 300 Kelvin? So if we were able to dye the particles and you'd be able to visually see what's happening, we should see an increase in their speed or their kinetic energy. Alright, so therefore we are expecting the pressure to rise because they're moving so quickly, so let's check and see what happens. So P1 we'd plug in 3.5 and T1 we'd plug in 100 equals. P2 is our unknown, so you notice that we actually have our unknown on the top, and that's fine. We can do that. We could actually have some of our initials as unknowns as well. That'll happen on occasion. And then we have 300 down here. And some of you might easily be able to see this. I'm going to do the whole math for this one, but you might be like, oh, well, it's going from 100 to 300, so all I have to do is do what? You guys could say it out loud. You'd be like, oh yeah, we're just going to multiply by 3 because 300 is 3 times 100. So I'm going to do the actual math though, so we'll do the cross multiplication and see if we get the exact same answer. So I'm going to take 300 times 3.5, and that's going to give me 1050. And then I'm going to take 100 times P2. That's a bad 0. There we go. Okay. And so naturally, I'm just going to divide by 100. I'm not going to show it this time. And this is also just moving decimal places. If I divide by 100, it brings the decimal back too. So this would just be 10.5. And the units, pressure was in atmospheres this time. So I'm going to label this as atmospheres. And there's my answer. I'll add a little on there for the M. Now you'll notice that if I was to take 3.5 and multiply it by 3, I'm also going to get 10.5. So it does work, but this is the amount of math and the type of math that I will actually want to see on your test and any homework. Alright, the last one is the combined gas law. So it combines all the gas laws. And you can see now that as I look at this, I have, if I circle these, a relationship between P and T. That's a Montan's law. I have a relationship between V and T, which is Charles' law. And I have relationships between P and V, which is Boyle's law. So you can see that all three laws kind of all come together in this, and we're able to, let's say I am varying all three of these, then that means that if I had pressure, temperature, volume, and the number of moles, then which one of these is not part of the equation, and that would be the number of moles. So you'll notice that the number of moles is held constant for each and every single one of these four laws. Alright. And so I added in here, so combining Boyle's, Charles, and Montan's laws for allowing for the development of a single equation, and you can see then we just kind of like added it all in. Okay, and P stand for pressure, V for volume, and T for temperature. Alright, so let's try it. Let's give you an example. So we have P1 is 3.5 atmospheres, we have V1 is 30 liters, we have T1 is 100 Kelvin, and P2 as our question mark, and give you V2 is 20 liters, and T2 is 300 Kelvin. So you would have all these in a problem, and as you're reading through, you'd be like, oh, I'm given two of these that are actually changing. So if I look at this, oops, as I look at this, I'd be like, all right, I can see I have a different number of liters once and twice, and I had a different number for my temperature in Kelvin from 100 to 300. So I'm just changing these and adjusting, and then I would just add in my numbers. So P1, 3.5, and you got to be careful with your algebra on these ones so that you don't make any errors. And V1 is 30 over T1, which is 100. There's a couple ways you could do these, and I'll explain once I finish writing out all of my knowns in here. P2 is my unknown. V2 is 20, and that's all over T2, which is 300. We'll fix that. Okay. So here's what I'm saying. If I'm looking at these, then I can solve this in a number of different ways. I could actually look at the left side of the equation, the 3.5 times 30 divided by 100, and I could find what that is as a value. And then I would look at the left side, and you would multiply the 300 over, and then you would end up dividing by 20. And as long as you're good with your algebra, there's no problem doing it that way or whatever way you would want to. I'm going to be consistent with what we've been doing so far, so I'm going to go ahead and cross multiply again. So this time I have three numbers to multiply. I have on the top here I have 3.5 times 30, but then I can also multiply by this 300. So I have 3.5 times 30, I'll type them in, times 300. And it comes out to a very large number, 31,500. And a lot of times just double check your math on your calculator in case you type it in wrong, something of that sort. And so that's what I'm doing right now. I'm just double checking my math to make sure that it's all good, and it is. Okay, now for the other one. This is tricky, and so this is called the commutative property of multiplication. So I can see I'm going to take 100 times P2 times 20, but once again, since it's all multiplied together, I can rearrange what I multiply. So I can multiply the 100 times the 20 and then times the P2, and that's what I'm going to do. So 100 times 20 is 20, and then you just add on your two zeros to make it 2,000, and that's once again times P2. So you can do that at the very end, so you can multiply your two numbers and then multiply times the variable. And lastly, I'm going to take 31,500 and I'm going to divide that by the 2,000, and P2 comes out equal to about 15.75. And since this is a pressure, I would come up here. I'm like, oh, pressure 1 was in atmospheres, so I know that this answer is in atmospheres. Okay, and so I can circle that as my answer. So that's how you can kind of look at all the different gas laws. So that was first looking at Boyle's law, relationship between pressure and volume. Then we went to Charles' law, which is a relationship between volume and temperature. Then to Amonton's law, which was a relationship between pressure and temperature. And lastly, the combined gas law has all three: pressure, volume, and temperature. Alright, so what's going to happen with this is you guys are going to have a homework assignment. That homework assignment is going to be due, and it will be collected by the substitute. But I also went through and I gave you an in-class assignment. So that in-class assignment is not a graded assignment, but it would be very beneficial and helpful to go through it. And so I'll create a video and I'll go through some of those with you guys as well, so you'll be able to visually see how to actually do some of these problems. Okay, so that's what you're going to be working on after this lesson. Tomorrow I will give you guys, or you'll have the in-class assignment available to you. You can kind of pick that up, and that way you'll be able to go through and work through the in-class first before you get to the homework, because I have all of the in-class as an answer key, and so you can check your answers on all that. However, the homework, you're not going to have your answers available to you. So that is section 2, and you have one more section left in the chapter.